going to be approaching a classic geologic problem here, measuring fault parameters and slip using a new set of eyes and tools, NASA's geodetic imaging data that you've already been introduced to, and the Geogateway online tools. Geogateway is a science gateway, which, as you've heard, has been developed with NASA funding. And today you're going to be hearing from 4 members of our nearly 20-member Geogateway team. My name is Lisa Grant Ludwig. I'm a professor at UC Irvine. I'm going to get us started. I will be joined at the end of the presentation by one of our UC Irvine students, Megan Mercanian, who is working almost finished with her MS, her master's degree. And in the middle, you're going to hear from Andrea Donnellan and Jay Parker of JPL. And Andrea is the Geogateway PI. So let me see if I can advance my slides. Okay, good. There we go. So what exactly is Geogateway? You're going to hear quite a bit about it in the next hour. I'm going to get you started with an overview. Geogateway is a science gateway that puts together both data and tools. So this is a convenient way or a convenient place for you to access a suite of online tools that you can use for data analysis, for modeling, and for rapid response using geodetic imaging data. So our main application of Geogateway is to analyze and model crustal deformation related to earthquakes and fault slip. Okay, so we developed it with that specific application in mind, but there are many other applications. The Geogateway provides not just data, but tools, and the main focus of those tools is analysis and application of the airborne InSAR data using the UAV SAR platform. Okay, you're going to hear a lot more about that today. That's already been introduced. The other main data type that we use and analyze with the tools is the GNSS, or the Global Navigation Satellite System. Those of you, many of you may also be familiar with that as GPS, which provides position, time series, displacements, and velocities. Now, although these 2 types of data and tools are our emphasis, we also provide other types of tools which allow us to put the data in context. The data can be layered. One type of data that can be layered is fault data. We'll illustrate some of that for California. Also seismicity, you'll see examples of that. Again, we will do illustrations from California. We also have some earthquake forecasting tools and some modeling tools. Okay, so as I mentioned before, the 2 main data types are the UAV SAR, which is the uses NASA's L-band InSAR. That is the longer wavelength that Heidi mentioned earlier this morning. And this allows for centimeter scale detection of surface deformation. Okay, so this makes it very useful for studying co-seismic and post-seismic deformation associated with earthquakes, as well as fault creep. But it has lots of other applications. The members of the Geogateway team have applied this for analysis of landslides, for levees, for subsidence, groundwater subsidence, other types of subsidence, volcanic, lots of applications to earthquakes, volcanic eruptions, wildfires, and wildfire scars. That's been a big topic of interest in California recently, as well as other areas in the West, and glaciers. The second main type of data, the GNSS, Global Navigation Satellite System, provides precision time series, a position time series, and there's data available on daily to sub-daily temporal resolution. The accuracies, the positional accuracies, are sub-millimeter globally, and so we can use these to measure deformation rates at 1 millimeter a year or better. Unfortunately, these stations are relatively widely spaced, so we don't have the kind of spatial resolution that we get with the InSAR. The stations are typically 10 kilometers or more apart, but Geogateway allows us to overlay data from both GNSS and UAV-SAR to give us a more complete spatial and temporal picture of deformation. Okay, so we use these other data types, along with the UAV-SAR and the GNSS. The USERF3 faults, that stands for Uniform California Earthquake Rupture Forecast version 3. I know that's a mouthful. The seismicity, and then we also have an option for users to generate KML overlays. So let me show you an example of our highest density coverage area. That's in California, because of course California is very tectonically active. We have lots of faults, we have lots of earthquakes, we have lots of deformation. So we have the highest data density in California. This is where we have the majority of UAV-SAR flights and flight pairs which produce interferograms. So you see these swaths here along the plate boundary. Also in black, you see the faults that have been digitized from the USERF3 data set. Although you don't see it on this image, there's excellent station coverage for GNSS and also a very dense seismic network. So California is an excellent place to utilize the Geogateway tools for data analysis. Okay, so although we have a lot of data, excellent coverage, and some great analysis tools, there are some limitations for Geogateway. Our focus has been primarily on rapid analysis of geodetic imaging data. Okay, so this is particularly useful for earthquake applications, but it may not be useful as useful for every type of application. We also find it's a major advantage to be able to image multiple data types concurrently and overlay them. Now, people who want to do a fuller analysis may want to download the data products from Geogateway and then do their analysis offline. Also, there are some limitations in terms of the uncertainty, the quantification. Geogateway has been in development for quite a few years now, and every year, all the time, we are continuously improving it. Several things are in the works. We do not yet provide stacking of InSAR products, and we have relatively limited user space, okay, but that is being expanded. We are in the process of upgrading our user interface. There might be some bugs, so please file bug reports. I'm now going to try to hand off to Andrea Donlan, who is the project PI. Let's see if I can make you the presenter, Andrea, and then she's going to go through UAV SAR. Okay, there we go, Andrea. You should be presenter.
Yep, can you see it?
Yes.
I'm going to, come on, try that again. There we go. I'm going to try to, here we go. Ooh, sorry. I want to use my pointer previous. Give me a second. Pointer options, laser pointer. Okay. Can you guys see my cursor?
Yes.
Okay. And I'm going to, I can't get rid of that. Okay. Got a lot of things taken up with the meeting, so I guess I'll have to work around it. UAV SAR, we heard about radar earlier, and mostly the spaceborne missions, although UAV SAR was mentioned. It's an airborne L-band, fully polarimetric radar. It's housed in the pod of a Gulfstream 3 aircraft that flies underneath the aircraft, and it points sideways. The interferometric radar images or interferograms are generated from repeat passes flown over a site of interest. In general, the radar observations are made from the swaths received, which are approximately 22 kilometers wide and are typically 100 to 3 kilometers long. This one may be 90 kilometers long here in Southern California. The reason we used UAV SAR was a couple-fold. One is I and my team members have been UAV SAR investigators, so we have a science interest in it. But the other, and this is changing now, and so we expect Geogateway to evolve over time, is that UAV SAR put out standard operational data products. And so to develop Geogateway, we wanted to work with data products that were systematically produced. So some basic InSAR concepts. I know it's a lot to digest. I learned a lot from Heidi's talk earlier. In fact, I want to go back through it, and I've been doing this for years. So if you have any questions, you can chat it, and then I can be interrupted by somebody to answer it. I prefer to answer as we go along if that's possible. So some of the basic InSAR concepts in Geogateway, what we're doing with it, relate to selecting data products, displaying individual lines. As you saw that map that Lisa showed, there were a lot of lines covering California. Changing the color mapping, using line of sight to extract information along profiles out of the images, downloading the products, and an example from the user guide. One of the reasons we focus on downloading products is Geogateway is very good for rapid analysis of data, rapid visualization, getting a good idea of it, but often people want to do further analysis of the data. So one is able to download the data product or the line of sight profile that was extracted and continue offline analysis. We also use that as a feedback loop. So if something becomes a routine that we normally downloaded and analyzed, then we work to implement that into Geogateway. So that help tab that Lisa showed, or file a bug report, please ask for features, or if you find something wrong, please tell us. So this is synthetic aperture radar on the Gulfstream 3. This is me for scale. The radar instrument you can see here is looking sideways or at an oblique angle. And it flies in these swaths, so the radar flight path is this direction. This is backwards because UAV SAR is actually left looking. This is from a spaceborne satellite. But the swath is the width of the swath or perpendicular to the flight path. And that's also called the range direction. And then we have the azimuth direction, which is the heading of the aircraft. Well, azimuth is perpendicular to the heading of the aircraft, but the heading of the aircraft then is forward. So we have these long swaths in the direction of the aircraft flight and with some certain width perpendicular to that. So what we are focusing on, what you heard about earlier was polarimetry and backscatter. and a little bit of interferometry. What we are focusing on is InSAR phase difference between two passes. So this is the upcoming InSAR satellite, which is expected to launch in the end of 22, beginning of 2023 timeframe. And we hope to update, we plan to update Geogateway to ingest the operational products from these other missions, such as InSAR. So if we have the surface of the Earth and the satellite or the aircraft flies over, there's a certain number of phases of the wave you can count, and then it's reflected back up to the instrument, we'll call it, since it can be airborne. So now the ground has moved. An earthquake fault has caused motion of the ground, and the second time we put the phases of the wave down, they come back up, we can count the number of waves, and there's an offset. So there's a difference here between this extra bit of wavelength compared to the previous image. So we combine those two images, and what you get out of it is this phase difference. So the extra wavelength is counted, and you can produce from that a raw interferogram, which is showing you phase differences of the waves. I like to explain it that if the ground doesn't move and the aircraft doesn't move, those waves overlie exactly the same. But if the ground moves, those waves will be slightly offset. And that's the fringe patterns that you see in these interferograms, because the phase changes spatially in map view across the image. So this is what we're measuring, is this ground change. Now in these images, everything's in the reference of the instrument looking down. So for Geogateway, we've turned it around because we're geologists and geophysicists, so we call it ground range phase. We're looking at the pixel on the ground relative to the instrument. So here's an example line of sight. I can't actually read what I have over here. Let me go to my other screen for a minute. So each pixel's displacement vector is imaged as a scalar, and then the projection of the displacement is in the line of sight vector. So what you can do is, if you know the wavelength, which we do, you can unwrap that, as we call it, to convert the wavelength to distance. So the wave is approximately 20 centimeters long, so one half cycle is 10 or 12 centimeters. And again, we call this ground range change. That's the motion of the pixel on the ground relative to the instrument. And if the ground is moved across this profile, then we can pull a profile out looking at these phase differences across the image. So that's line of sight. So to select the data products, one goes to geo-gateway.org. We are in the middle of transitioning from our older site to a new updated site that's more in line with best practices of today and other science gateways. So when you get onto geogateway.org and there's a hyphen there, you'll see a message up here that says we're migrating our site. There is a link within there to the beta site, so you can use either sites right now. The beta site will be transferred to operational very soon, so we recommend using that one. So once you've opened Geogateway, it'll open in a map view. We focus it on the Western US because that's where most of our users are working. You can click on the UAV SAR tab up here, and then you can show overview of the lines. Here, you can select by point or rectangle. In the old interface, it's across the top here, but it's the same idea. You can select it, draw a box, or select a point of interest, or you can put in flight name path if you know the flight number, which we do because we work with a lot, or latitude and longitude. So I had an intern working on landfills, and he just wanted to focus on these little tiny landfills. So he asked us to add this feature, and it's an example of how you can ask us to add these features, where you can search by latitude and longitude, and then all of the products will be displayed. So these are all of the available products, and then once you select the data products, you get a shorter list. So we're missing that here. Once you've selected those products, you get a list of just those products in the view that you're interested in. So for latitude and longitude, every swath that crosses that point will be available in a list. So we've selected by flight name path up here in this specific case, so we get one interferogram. You can select your interferogram of interest. And what we've done here is change the color scheme. So probably people are very familiar with interferograms and these pretty purple, blue fringes and pink. We've changed it both because we find the contrast is easier but also it's better colorblind scheme for colorblind people. So we have options so people can change their color scheme. And here you see all these different lines. You can click the checkbox for the interferogram of interest. Let's see. Next slide then is you can draw a profile across here. So all the user needs to do is click on the plot, and a profile, a default profile length will come up with a point A and a point B, A being on the left of the plot, being on the right side of the plot. These endpoints then can be moved around. And what we're extracting then is the ground range change in distance units, in centimeters, across this profile. And here we have the Napa earthquake through here. This is the fault that ruptured. And you can see that we have line of sight range change that meets a discontinuity where the fault is. There's a big jump. And then we continue far field. It's similar because, again, these faults move like this. We don't have big tectonic block motion. And you can figure out then the line of sight displacement across the plot. Now, what we haven't implemented yet is converting that to horizontal or vertical measurements. So outside of Geogateway, you can download this plot. And if you want to do a projection onto vertical or horizontal motion, then one can do that. And we've done that in this particular case for a paper by DeLong et al. In 2015. You can change parameters on the endpoints either by dragging these endpoints around or by changing the latitude and longitude in this box. You can also manually change the line length. So if you're making plots for a paper, you may want this very specific, say 5 kilometers, and your azimuth heading exactly perpendicular to the fault. So you can fine tune these parameters. And we've set up Geogateway so that you can actually take screenshots and have publication ready plots or figures. And we've done this many times in papers. The other thing that's kind of handy is you can set the layer opacity by dragging the slider here. And that will fade out the interferogram so that you can see the underlying topography. And what I think we're going to talk about later is outside of the UAV SAR tab, you can click on and off those faults that Lisa showed you. What you would see in the case of the Napa earthquake is the fault, mapped fault, is actually displaced to the east about 3 kilometers from the actual rupture. So that's very handy. And let's see, the last thing is down here, as I mentioned, you can download the data. So there are 2 things that you can download. You can download the profile, as I mentioned, or you can download the data itself. So you can download that interferogram, open it up in Google Earth, or run your own processing on it to do additional work. So to download products, it will take you to a new window. It will tell you the description of it, the times of the first and second acquisitions, how many samples, terrain height. The main things here are the peg head. That's the initial position of one of the corners of the interferogram, and then the radar direction and the radar wavelength. So it's almost 24 centimeters. Over here on the right, then, you can download all of these products. This will take you to Earth data at ASF. It will take you to the Alaska Satellite Facility DAC. So when you click on one of these products to download initially, if you don't have an Earth data account, you'll need to create one. If you do, but you haven't used it in a while, you'll need to log in, and then it will take you straight to this and download the product that you need. So just be aware there's some intervening steps here. We've now handed off that process to ASF. These KMZs of ground range interferogram are very handy. You can download it, and as you zoom into higher levels, you get much higher resolution of your image that you can view. So that's kind of nice. You can also look at correlation and other things as well, and the metadata, and then there's a description of the data format. Let's see. So here's what I just talked about. So when you click on that, so if we just click on, just say KMZ of ground range interferogram, you'll be taken to the Alaska Satellite Facility. You can either register or log in. It will redirect you directly to that site, and then you can download or just open up the file. This is something we had, and as we're migrating to the new site, it was turned off, but it will be turned back on. It's a very handy feature for fieldwork if you have internet connectivity, of course. So here's a case where in the La Habra earthquake, we saw what looked like this offset. In the interferogram, you can see this here. An interesting aside is that the the earthquake, the main earthquake, the epicenter of the earthquake was up here in La Habra. We have a paper on this, but these two interferograms looking at different directions collected at different times give us a lot of confidence that there was motion here in the West Coyote Hills. It turns out it was about 10 centimeters of northward motion on an unconformity about 500 meters deep. So it shows you the kind of modeling and analysis you can do with these data. But we found this offset here, so we drove to it. We knew where we were on the image, and it turned out, here's my car parked, there's this left lateral offset of the road. And we, Lisa and I and a couple other people, spent a day using this interferogram to go out in the field after the La Habra earthquake and find a lot of features like tenon curves, etc. UAV SAR was used extensively in mapping that El Mayor-Cucapá earthquake and finding all the small displacements on the Yuha and all other faults. So again, if you had an iPad with location awareness, this would be very helpful in the field. So we will be bringing that back, and it seems very relevant to GSA type audience. So for UAV SAR example then, if you guys want to follow along, you would click on geo-gateway.org, click on the UAV SAR tab. I always, when I'm doing it, I click on Map Tools first. I show the USURF 3 faults for California because I'm more oriented by faults than locations. So that's a little pointer that you may want to do. And I always set it to gray because it's a little easier, it's a little more muted and easier for me to visualize. So you click on the UAV SAR tab and then check Show Overview. This is in the new site. In the old site, you just click on the line altogether. And then you can search for an interferogram. As I mentioned, you can put in the flight name path directly if you know what you're looking for. So if you want to see all the San Andreas lines that were collected, for example, you would just type San Andreas in one word. Or if you know the flight name, like 26501 is one I use all the time for the El Mayor-Cucapá earthquake, I just type that in and all those lines would come up. Or you can search by latitude and longitude, and that will give you all the flight names, flight paths that cross that one point. Again, as we mentioned before, there are options to draw an area or drop a pin. In the new interface, they're on the left side, and on the old interface, they're at the top of the window. So then once you've selected your area, so you've selected an area, say I put in 26501 here, my favorite line. This is the El Mayor-Cucapá earthquake. It mostly ruptured in Mexico. This line is cut off at the border because at that time we weren't allowed to run UAV SAR in Mexico. Now that's changed. You can see this displacement here. We also like the full color scale because it's easier to tell what's moved in what direction, whereas fringes are very hard to count because you have to know which way the fringes are going. So you can show that. If you make an line of sight plot, you can hide or show it. Again, as I mentioned before, you can also put in latitude and longitude of either for searching or for the line of sight tool. So now we've clicked on this map. We've gotten a profile. You can adjust these endpoints. A is on the left side of the plot. B is on the right side of the plot. You can specifically put in latitude and longitudes. You can change the line length and change the azimuth. And again, in this case, the lower layer opacity is faded so that you can see the underlying terrain and the underlying map under the interferogram. Another thing I should mention is that if you click on a different image then, you'll have that same line of sight profile. So if one wants to look at coseismic versus post-seismic displacements, you can change the image here and the line of sight profile will change as well. And now I'm going to hand it off to Jay. I guess I have to turn off my pointer. Give access to Jay Parker. Did you get it, Jay? Do I need to maybe stop that? All right, Jay, I think you're in charge.
Okay, now I
Can't
have my
hear
mic
anybody.
on. I think you can hear me. And
Yeah, how do I stop sharing? Or you just start, I think.
I think, let's see. Good, thank you. All right, so I want to go to full screen. So I need to go here and here. Sorry, current slide. Okay, I think you can hear me and I think you can see the screen. Let me know if you can't. I can't see the chat, so if anything comes up on chat, please alert me to that verbally. So we're going to talk about how we display GNSS, Global Navigation Satellite System data. We're taking the GNSS data from the JPL Analysis Center, and all they use for GNSS are the American GPS system. There are other systems that are currently being analyzed by various people, but right now what JPL is presenting is GPS. So we're going to use GNSS and GPS a little bit interchangeably. So I'd like to introduce this very simply for anybody who hasn't thought about it too hard, that you all are familiar, everybody in the world practically these days is familiar with GPS in the sense that they use it on their phone, right? You might want to know, what do you know if you have GPS on your phone? Well, you get a little blue dot on a map and it tells you where you are. So GPS tells you where you are. But also, if you're a runner or a cyclist, you might have an app on your phone, and it actually can map out where you have gone. So GPS is also useful to tell you not only where you are, but where you were, and to map your motions, and even to determine if you're a runner, it might tell you how quickly you travel down one street or another, and that you're getting slower as the day goes on. So bear in mind that that's what we use it for. Now in this image, we have a very high-end GPS antenna, and it is drilled and braced down into this rock outcropping. So you have to ask yourself, what do you know if your GPS is attached to a rock? I like to puzzle people at JPL Open House and get teased out of them that from what they know already about GPS, you know where the rock is. What good is that, right? Well, you not only know where the rock is, but you know where it's been. You get to see it move, which is plate tectonic motions. And typical plate tectonic motions are about up to a few centimeters a year, which is roughly the rate your fingernails grow. So this is why geodesy is such an exciting field. You get to see extremely slow motions on the Earth. So we're going to show how the Geogateway system displays velocity. We're going to be focusing on the Elmar-Kukapa earthquake at first, and we're going to show the background velocity apart from the earthquake, the coseismic change in position, post-seismic displacement, model, reference station, and product download features that go with GNSS. And part of the main point of this is that you can display the GNSS along with your interferograms, your faults, and other information to get an overlaid set of images that show your context. So to get to the GNSS tool, you simply use the GNSS tab in your Geogateway system, and you select velocities or coseismic, post-seismic displacement model. We'll go into all of those in a minute. You would typically draw an area on your map. Usually I'd use a rectangle for that for GNSS. And when you draw a rectangle on the map, it will fill in for you the latitude, longitude, width, and height in degrees of your box. And if you want to customize those from your initial box, maybe make them exact longitude and latitude integers or something like that, you can do that. That's quite easy. Another thing you can do is pick a reference site, and for this example, the reference site CCCC is somewhere up near Northridge. So it's basically showing motions in the Los Angeles basin that are relative to a point that's really up, it's kind of still in the border zone, but more on the North American plate. You can set the size of these vectors by setting the scale parameter. What the scale is the number of millimeters of motion per year that correspond to a degree of arrow length on your screen. So 320 millimeters per year per degree is the scale. That means if you want to make the vectors longer, you use a smaller number. So if you use 80 for your scale, then 80 millimeters will be a pretty good long vector up to a degree long. And 8 millimeters will look like 1/10 of a degree and it'll be a decent sized arrow. 320 works very well for the velocities in the Southern California area. You can also select somewhat the marker size. This one says minimize marker size. There are little markers for every GPS that are little tiny dropper markers that you can hardly see here. If you don't say minimize, then you can see them more clearly. And include error ellipses. So these vectors, we'll get to this in a minute in more detail, but they are anchored at a red or a blue spot, and then at the other end is a uncertainty error ellipse, which are very small for velocities. Velocities are typically determined over the entire time series of the GPS that's been collected. I should mention we're using daily time series, and many of these are 20 years or longer time series, so the velocities are extremely well determined. So what are we showing again? Each vector shows the velocity of a single GPS station. The length of the vector shows how fast the GPS station is moving. Vertical displacement is shown by red or blue circles, red for up or blue for down. The larger the circle, the greater the displacement up or down, and the longer the vector, the greater the displacement horizontally. If you click on one of these circles, you will pop up the JPL Analysis Center image of the GPS time series. So this is handy for a number of things. If you click on it twice, you get a bigger image of that time series plot. So this is simply the daily time series in 3 dimensions of that GPS station. We said that you know where you are and you also know where you've been. So the 3 strips are marked latitude, meaning the northward motion, the longitude, meaning the eastward motion. This one is going negative eastward, so it's going west. And the bottom graph shows the vertical height in centimeters versus time in years. And the vertical is typically relatively constant. There are exceptions. I know a case where there's a narrow valley where they were pumping well water like crazy during a drought, and it just dropped pretty fast on this scale. So it's good to be able to pop up these for background information so you can get an idea how stable the site is that produced that dot and that arrow. And that way you can discount some of them if they seem to be out of place but look extremely noisy or extremely disturbed in their time series. So the velocity vectors, again, are shown as green vectors with error ellipses. The vertical displacement is shown by red or blue circles, and the larger the circle, the greater the displacement. So this plot does not have a reference site. So what does that mean? That means you are getting the velocity vectors in terms of a global reference frame. In this case, the IGS 14 reference frame, which is linked to the ITRF 14 reference frame. So it's just giving you have to understand that velocity is always a matter of velocity compared to what. If you are walking up and down on the deck of a cruise ship, you might want to know your velocity with respect to the deck, or you might want to know the velocity of the cruise ship that is traveling around the world. And both of those are part of your velocity in some larger frame sense. So you can have it in the standard global frame, or you can have the velocity with respect to some reference site. For example, if you want to know the motion with respect to the Pacific plate, you could choose your reference site on Catalina Island. You'd have a pretty good approximation of your motion compared to the Pacific plate. Or you could pick a site in Kansas and have your motion with respect to the North American plate. when there's an earthquake, you can get one of these Aeroplots, very similar format, that shows you the change in location from before and after the earthquake. And that means the scale means something different here. Instead of 320 millimeters per year per degree, now it's just 320 millimeters per degree. So we selected an area that had a lot of displacement in California from the El Mayor-Cucapa earthquake in Mexico. And for the coseismic plot, you can see that the big effect was that this area was pulled to the south by the motion of this 7.2 magnitude earthquake in Mexico. You can also see that most of the stations moved upward in this area, but there's also a region where sites move downward a little bit right at the time of the earthquake. And then if you select the, and you can, one of the things I should point out is that for this coseismic option, another feature shows up, which is to choose the epoch. So the epoch is the date of the earthquake, and you need to look that up and just insert that. If you look up an earthquake by name in Google, you'll probably find the date pretty quickly and can just insert that. And then for post-seismic analysis, sorry, there we are. You get to pick how long of a post-seismic period you're interested in. And for this plot, we're showing both of these at the same time. So these same arrows for the coseismic are shown here as well, but there's also some new arrows showing that this site that moved to the southwest during the earthquake is now moving much more toward the south after the earthquake. And that this site that moved this far during the earthquake has moved this shorter distance during the post-seismic time. And now you can see that the error ellipses are getting to be more noticeable because we're using a shorter time scale to estimate these displacements. So as an alternative to a coseismic time period, you might have an area where the post-seismic is starting right up and showing large amounts of creep on some fault right after an earthquake, and you might want to get closer into the time of the earthquake. You can just pick two dates, and that's what's shown here, epoch 1 and epoch 2, and some number of days that you're averaging for each of those two dates. So these 9 days are centered on March 30th, and these other 9 days are centered on April 10th. And so you can get a slightly different estimate. These arrows are not really very different in this case, but it does give you a way to fine-tune your analysis. And then also there's a method called model, which is an alternative to the coseismic, and this uses a JPL analysis center fit model that is the background velocity and the breaks that are detected, and also some seasonal information. So you can get another alternative, which also doesn't look very different in this case. The downward motion of this site comes out a little bit differently, for example. And so these give you some different ways you can kind of fine tune your analysis and check different possibilities. Once you produce an Aeroplot, well, before I mention that, where do we get this data from? So we have a link to the GNSS time series source page. This takes you outside of Geogateway, but this is the JPL Analysis Center page where you can see a very dense porcupine plot of the motions of the sites in California. And as you zoom in on this, it actually fills in more sites. And you can pick a site by name and get the time series plots, and you can actually get the full time series data from this site. So if you wanted to pull out a time series, all of those points that were on the daily time series plot I showed earlier, this is where you can get that from. If you want to take your arrows that you plotted and download that data as a KML file, you can do that as well. That's an option on the same page of the Geogateway page. And that way you can save your results, you can replot it. We mentioned that there's a mapping tools tab, and under that there's a KML uploader tab. So if you save your velocity vectors or your coseismic vectors, you can then redisplay them in Geogateway later through the KML uploader. Another feature that is really just piggybacking off of work that USGS has done is to display seismicity on your plot, and this is another layer, so you can display this at the same map with your UAV SAR, your GNSS. So one of the features is you can just take the feeds from from USGS, for example, the magnitudes greater than 2.5 for the last week, and put that on your map, and that'll come with tooltips. So if you click on one of these, it'll give you some detail about the earthquake, when it was, and the magnitude. But what we use a lot more often in conjunction with UAV SAR is we can use the second feature, where again you can select a box for an area, draw an area on the map, and then select a start date and an end date. So one of the things you might do is select your 2 visit dates from your UAV SAR image, and this will give you all of the seismicity that happened between the 2 dates that the airplane visited the region, which means it's all the seismicity that's reflected in that interferogram. So you have to put in those dates by hand. Those dates are listed on the UAV SAR table that came up earlier, and you need to give it a minimum magnitude. And you need to be a little bit cautious about this. If you're including a major 7.2 earthquake or something like that, and you ask for a minimum magnitude of 2, you'll be waiting a long time, and it might even cause the system to jam. So be careful with that. If you're in a time when there haven't been major earthquakes, magnitude 2 and up are great. If you're looking at aftershocks of a major earthquake, you might want to go with 3.5 or 4 for the minimum magnitude. So these things can be used for multi-method layering, and I have 2 examples that are in the slide deck here. One of them uses UAV SAR, which is shown in the background here, with the profile tool, and also the seismicity layered on top of that. That's these dots here. And also the USER3 faults, which are shown as these kind of black thin lines in this plot and up here. So the idea here is that we started out in UAV SAR and we said, okay, I see that major southward motion we found out from the GPS. This is southward from the Elmire-Kukapa earthquake, but there's something anomalous going on in this section right over here, and that corresponds to this area of the map right here. And so we said, well, what could that be? And we looked at the aftershocks, which were included in the first few days after the earthquake, and that didn't show a lot of activity there. And then we said, well, maybe we should look at the time from the beginning of the interferogram right up to the earthquake, but not including the earthquake. And it turned out there was a seismic swarm going on right in this area in November, several months before the Elmire-Kukapa earthquake. And we said, well, what fault could be responsible for that? So we turn on the USER3 faults, and we click on the fault and get this tooltip, and we find out it's the Cerro Prieto fault that likely has an extension up into this area that is subsurface and possibly gave rise to these swarm of small events. Also, the swarm of small events, you can click on those and get individual readings on individual earthquakes if you zoom in. Another thing you can do with multi-method layering is you can pull in information from the KML uploader. So the idea here is you may have special information that you can make into a KML file, for example, survey sites that you took in the field, and you want to overlay those with the UAV SAR image. So I made a KML file out of slip waypoints that were taken by field survey right after the time of the Elmire-Kukapa earthquake that were published in the USGS open file report listed down at the bottom here, and found that there are quite a number of sites that were surveyed right after the time of this earthquake that the effects are shown in this interferogram here. And a number of these small bumps in the interferogram correspond to places where they discovered surface fractures in the field surveys. In fact, the order was the reverse of that. We produced the interferogram early on, and the field survey people were able to use that to figure out which sites to survey. Another thing that illustrates the use of this for kind of exploring the data is you can include the UAV SAR image along with seismicity. I'm actually not showing the seismicity in this plot. I got a little too busy. But here I also have the product of an edge detection analysis. That is, again, it was done outside of Geogateway, but I was able to take the KML from that and upload it. And now we're zoomed way in on some of these sites that were on the western part of the previous plot. And one of the interesting features is that our edge detection seemed to be detecting two different fractures on the surface that were only about 400 meters apart. And so it's interesting to take our profile tool and to see how that actually looks in the values in the interferogram. And indeed, you can see a jump at about a half a kilometer from the beginning point A, and another jump here at about 0.9 kilometers from the beginning. You can see how big those jumps are. Again, this is in the radar line of sight direction, but it gives you a very good idea how far apart and what size these jumps are that we were seeing in the analysis. And then I also have the slip waypoints shown, again, indicating that California Geological Survey knew about both of these fractures and surveyed both of them at the time. Hang on one second. Yeah, if I'm going to, before I turn this over to Megan, I'm going to do one more thing. And that is to show an example of, this is the live Geogateway interface. And what I've done here is I've made Mount Wilson the reference site. So the sites on toward the North American plate have pretty large arrows, but since Mount Wilson is on the other side and it's right in here, sorry, up in here, we've taken out the main Pacific plate motion, and now you're seeing the variation in motion aside from the Pacific plate motion all across the Los Angeles basin. So there's a lot more detail that shows up if you use a reference site that's carefully selected. Another one that I'll show is overlaying the GNSS vectors with the Napa earthquake interferogram. So this shows you the GNS vectors are relatively sparse, but they do show the kind of the motion you would expect for a strike slip earthquake. You can see the arrows are kind of curving around on this side this way, and they're bending around in the opposite curved direction on the other side, focused on the main rupture of the earthquake here. So with that, I'll turn over discussion to Megan.
Okay.
Jay, you also had sorry, Megan. Jay, you had a question in the chat. It says, from a technical standpoint, phase differences represent fractional wavelength changes. What happens if and when there are displacements greater than a single wavelength?
Okay, two things. You can hear me? Okay. Two things. One is that part of the UAV SAR product is an unwrapped interferogram. And so the 2π ambiguities in phase have been resolved by considering the entire map of phases and connecting things where they're easy to connect and progressively connecting more areas of the map so that most of the map is filled in. There are some holes in those maps where there's too great a disruption in the phase, for example, from agricultural land that's been plowed and replanted in the meantime, or in bodies of water. The second thing is that if there's a earthquake that cuts all the way across the interferogram, which in fact happened for the Napa earthquake, then it's tough for the phase, the unwrapping to do a perfect job on the whole image. And you get connected phase on both sides. That's fine. You can do use the profile tool in either side and get relative phase, relative displacements on each side, but the displacement across the fault may not have the correct number of cycles added into it. And for this, the plot that I showed of the Napa earthquake, we had actually done a custom job of fixing that right on the fault. So actually in that plot, we're showing the correct phase jump across the earthquake fault, but that took some custom manipulation behind the scenes.
Okay, I guess I'll get started. Can you guys see my screen?
Yes.
Okay, cool. Okay, so to seek further guidance on how to navigate the GeoGateway website, you may refer to the GeoGateway user guide. And within the user guide, the hosted data sets and models accessible on GeoGateway are presented and described, and there are also sample exercises to allow users to gain a hands-on experience. And so to access the user guide, you must navigate to the GeoGateway website. And as you can see here, there are two different websites. And as mentioned before, GeoGateway has recently transitioned into a new interface. And so the first link is the website to the old interface, and the second link is the website to the new interface. And so currently the user guide is compatible with the old interface, but shortly it will be available for the new interface as well. So I'm going to click on the old website. And as you can see, it navigated me to the website. And once you are in the website, there's a pop-up message that allows you to navigate to the new interface. And so this is the new interface, and I'm going to go back. As I mentioned, the user guide is within compatible with the old interface. And so once it's available for the new interface, it will be available in the Help tab. And so for now, the user guide is within the old interface and available in the Help tab. And you can download the full document, or you can download a document based on what your interests are. So for example, if you click on UAV SAR, it downloads as a PDF, and you may run through the PDF. And then also, just to mention, we have exercises that will allow you to better understand the website and GeoGateway as a whole. So I definitely recommend going through those. And in addition, our team is currently on the work to preparing tutorial videos that will help users navigate through the website as well. So that will be up shortly. Okay. So in conclusion, as we noted, GeoGateway is a data product search and analysis gateway for scientific discovery, field use, and disaster response. GeoGateway focuses on NASA geodetic imaging products from InSAR and GNSS integrated with earthquake fault data sets, seismicity, and models. And to know, as you can see, this is the user guide, and this is the table of contents within the user guide. And we talked about a few of the tools, but in addition, there are other tools available. So I definitely recommend navigating to the website to see what other additional tools there are. And yes, so.
Okay, questions. Is the guide exercises for the beta site or the old site? It is currently for the old site. But the main and the new site does the same thing as the old site. It's just that the layout is a little different. So Megan is starting to update the user guide for the new site, but that is not available yet. And I see that question was from someone at a college. I think that the exercises in the GeoGateway user guide are really a great resource for instructors if you want to incorporate any of them into your classes. Andrea has used them in classes as well, and they're not just confined to California. You can explore the data that's available through GeoGateway. There's some nice UAV SAR data in Hawaii that you can use. It's not just for faults and earthquakes.
Just a few of the interesting UAV SAR collections outside of California include the Slumgullion landslide in Colorado, studies of Iceland and Greenland. There's some areas in Central America, and Hawaii is very interesting. There's also some data collection in southern Japan and some other places. That's all available through the Geogateway interface. We just focused on California for convenience, but the whole world is there if you back out.
And I'd also just like to add that we have a rating system that is migrating into the new system, and that's so that more novice users can have a sense of what are good data products, because we show all the data products, and some may have artifacts like errors introduced from water vapor in the troposphere. In the back end, we've also been working on developing better processing to mitigate some of that, and so that is going to be implemented into the new products that come out. But just wanted to caveat that some of the products are better than others, but we're trying to update that and keep those rated. And if you have questions about how to use them or what to interpret, you can send a feedback report or contact one of the team members so that we can help you interpret the data better.
Okay, question: how might these data collection methods be used for planetary geology?
Well, we don't have data on other planets, but you could use these data for analogs. So some of the structure for motion or stereophotogrammetry that we have as products that we haven't emphasized a lot in the system yet, some of those have been used for Mars analog studies. And so you might do the same with some of the radar products or other products as well, but there's no data that we have for planetary bodies.
This is the new interface website, and so basically you will have to click on the report a bug tab, and once you're on this page you have to choose what you are reporting. So if it's a bug, feature, enhancement, or other. And so let's say we are reporting a bug, we click on that, and then let's say we are reporting a bug on the UAV SAR tab, so we click on that, and then I'm just going to write test for now. And then you could also drop screenshots or files to allow them to get a better understanding. And then once you're done, you click on that and you're all set. And you could do that again if you find anything else or want to recommend any enhancements or other details. On the old site, within the help tab, you can find the user guide and then other material as well. And as I mentioned, you could download and find what you're interested in or download the full document. And yeah, and soon we'll have the help tab within the new interface once I have changed and made everything compatible to the new interface.
And there are
Actually,
exercises.
we also have that report issues on the down at the bottom. It's still there.
Mm-hmm.
Yeah, on the old site. I just wanted to show that there are exercises you can download that students can do if if a piece of this is taught in a class, for example, or if you want to walk through an exercise just to understand it better. And this will all get moved over to the new site.
Yeah.
Right, and there are different exercises. There's a moment magnitude one, some on GNSS, and then also for UAV SAR. So definitely walk through these. They'll help you gain a better understanding.
And we had talked about a quick demo of the moment magnitude tool. If you want to just go show that really quick, because it's handy, simple tool.
Okay.
Over there, go back to the Geogateway site, just to the Geogateway site.
Okay.
And click on magnitude.
Okay, and so for the default, it's,
Oh, go ahead. I'll let
yeah.
you go, Megan.
Sorry, I didn't hear that. What was that?
Oh, I was just going to say that magnitude is related to the dimensions of a fault and the slip, and then the rigidity of the surrounding material. And so you can show how we started with a Tohoku earthquake example. You can change those parameters and then calculate the magnitude. So if you just push calculate, you get both the seismic moment and the moment magnitude. So it's a handy little way if there's, say you want to do the opposite, there's a magnitude 6 earthquake, you can change these parameters for length and width or whatever you may know about the earthquake to get an idea of the dimensions of the fault.
Yeah, this is a little tool on the side. So if you're looking at an interferogram and you see you think you can estimate from the interferogram or from the GPS the length of the fault, and you know from seismic reporting what the magnitude was, then you can check whether the depth makes sense and that all fits together, or it's a way you can do consistency checks and to test hypotheses on things you might be deducing from what you see in the maps and the map data.
Yeah, it's a basic tool for modeling with the data, and we have found that it's quite popular among users. It's just a convenient resource. Some users return to our Geogateway site just to use the moment magnitude calculator.
Right, it doesn't tie in with the maps in any other way. It doesn't pop up any features on the map when you do it. It just is something on the side.
Yeah, but you'll see in the user guide, there are some examples of how you might use it for understanding the data and for looking at the significance of the deformation and fault slip.
One way that I wound up using it very early on was after the huge earthquake at the day after Christmas in Sumatra many years ago. I was trying to figure out the dimensions of the earthquake from data, and nothing was working out right, and I couldn't figure out why. And then I realized that the earthquake was at such depth in the trench that the shear magnet modulus was wrong that I was using, and I had to look up what that would be in the trench and put that in, and then it made more sense.
Okay, I guess we need a disclaimer over there about shallow versus.
We have a default value, and you have to fill in the real value if you know it might be different.
Yeah. Oh, is the data restricted to California and Colorado? That's the question, and then the questioner answered that. Disregard that part of the question. I found more in other places. Yes, there is data. I mean, it's a global data set, but the density of data is by far the highest in California. But there's some interesting things if you explore. You'll find a lot of interesting spots.
And I should mention all of the GNSS data are available globally. As investigators are funded to investigate other places of the world with UAV SAR, that will just automatically show up in Geogateway. There's no additional steps that need to be done.
it would be helpful perhaps to mention again that what we're displaying for UAVSAR on the map is always the unwrapped interferogram. If you follow the link to the data source, then you can get many other products that go along with that same strip, like the backscatter reflectance and the coherence and the wrapped interferogram, and you can see all of those in both KMZ form and the actual binary data in a big binary file that might be a good fraction of a gigabyte